Welcome to the information session. I am Professor Hongzhou Zhang. I am the Director of Teaching and Learning for postgraduate students at the School of Physics in Trinity College, Dublin. For today's session, I will start with an overview about the government postgraduate scholarship scheme. This will be followed by several research talks. I hope you enjoy today's session, but most importantly, I hope you will find a supervisor to work with to apply for the scholarship. If you have comments and questions, please ask in the comment area. We will try to address it here. You are also welcome to email the academics whose research interests you to initiate detailed talks on the research project. Well, now let's first talk about the scheme. The IRC Postgraduate Scholarship is a prestigious award. This also means it is very competitive. The successful rate from last year is about 18% for European students. This is even lower for non-EU international students, it's about 5%. However, this is not zero, so I would encourage exceptional international students to apply. The successful rate from candidates supported by our school is 40%. As you can see, this is much higher than the average. To apply, you must have a first class or upper second class grade from your undergraduate program, or if you have a master's degree, you are eligible to apply. Of course, there are some other eligibility requirements. Please refer to the core document for the details. If you are successful, your award and the PhD program will start from the 1st September 2021. Well, how to apply? Each applicant can only submit one application. Since you are the applicant, you must take responsibility to complete and submit the online application to IRC by the deadline. To complete the application, you must fill several online forms, which for your part is more or less like a CV, but you need to write a personal statement and also career plan. The most important part of the application is a research proposal. To write a competitive research proposal, you should work closely with your supervisor. Of course, your supervisor need to express their support explicitly to IRC by filling their own forms and submit it by the deadline. You also need to coordinate 2 reference letters from 2 referees who knows you. Please note the deadlines. You must submit a completed form online by 29th October. That's very close, so please act now to engage with your supervisor to work on the application, the proposal, and your statements. You need also to remind the supervisor and the referees to submit their parts by the deadline. Well, that's the key information concerning the application. Now let's start our research talks. Hello, My name is Hongzhou Zhang. The project is to enable two-dimensional neuromorphic devices. Let me first talk about the challenges this project to address. So we know for the past 40 years, electronic technologies have changed our lives. Okay, so the success of this technology we know is based on large-scale integration of semiconductor devices. So the whole success of this electronic era is based on the continuing scaling of the device to make it smaller and more powerful. However, this scaling soon will hit its limit. So this is the most pressing challenge faced by the semiconductor industry. The industry will need a technology to replace the conventional device. There have been extensive research on this. However, by far, there hasn't been a solution to this scaling problem. The overarching aim of our research is to enable the device application of nanostructured materials for this emerging computational platform. So specifically, this IRC project is to enable a new two-dimensional resistive switch which can hold its resistance states. This device is called micro-resonators. There are actually extensive research on this micro-resonators, but the challenge is the device variability. So that means the device performance varies from one device to the other. This is a showstopper since this issue is not compatible with large-scale integration. So the IRC project is to deal with the device variability issue. So we propose a solution based on a new fabrication technology that is called the helium-ion microscopy. My group here in Trinity have been working on this technology for 10 years. So in a helium-ion microscope, a helium-ion beam is accelerated, focused, and delivered to the spaceman where the incoming ion can knock out the material atoms and leave a vacancy there. So the key advantage of this tool is its ultra-fine probe. So this means we can control the location, size, and type of the defect being introduced in the material. So there have been extensive research conducted concerning this ion-matter interaction. However, there is still a huge knowledge gap regarding the interaction that occurs at a highly confined region. The controllability in material modification will not happen without this knowledge. So this IRC project is to address this key challenge in the helium-ion research. So what we are going to make is a device like this, okay? So it's based on two-dimensional layer of molybdenum disulfide, electrically contacted. So these electrodes are put there by electron beam lithography. Okay, and then the material is irradiated by a focused helium-ion beam. After the irradiation, we will conduct a range of characterization and electrical evaluation. Okay, so this is an image of the device by the atomic scanning microscope. The device after the irradiation shows this resistive switching. So this is quite promising since we know for sure the ion irradiation can introduce the resistive switching. However, the switching mechanism is elusive. This IRC project aims to collect experimental evidence to clarify this mechanism. To understand the mechanism requires detailed knowledge of the materials and the effects introduced by the ion irradiation. This is indeed an interesting puzzle the IRC project will tackle. We will conduct advanced microscopy. For example, here is an atomic resolve image taken by the transmission electron microscopy. The microscopy results will be corroborated by optical characterization here. Okay, so these results will, of course, be linked to those from the electrical evaluation. We will then synthesize the knowledge of the ion modification and the switching mechanisms. So this project is to address two important challenges The project is based on our 10-year achievement in the field, and we do have very interesting, promising results to validate this idea. So again, I would mention that research is experimental based. You will develop knowledge and hands-on skills in material deposition, electron beam lithography, and also a range of advanced characterizations. You will gain insight in the electronic process in 2D materials. I would like to thank you again for your attention. If you are interested, please send me an email. I will be very happy to discuss the research with you. Okay, good luck. Hope you enjoy the day.
Okay, hello everybody. I hope you're enjoying the day today. This is a presentation from my own group, which is the Computational Spintronics group. And this is a materials modeling and, if you like, a quantum physics group here in Trinity College. This is a picture of the group taken a couple of years ago. And this is, unfortunately, the picture of the group taken now, where we, of course, go online for our meeting and so on. Hopefully we'll be back soon in class. So the interest in my group is in materials modeling, and recently materials modeling has been taken by storm by another type of technology, computational technology, which is called machine learning. Now, machine learning, you might have heard about it. It's a branch of artificial intelligence. And the main idea of machine learning is relatively simple, is the ability to navigate data. And typically what you try to do in machine learning, you try to construct algorithms that take information in a form of a vector, some type containing a number of quantities, and you try to correlate this vector with quantity that you know. So you try to establish relation between the data. Now, this is, of course, this is a huge field in computational science, and the simple concept that I gave you here, so just to try to establish relation between data, is just a small fraction of what machine learning actually does. And you might have heard about a number of applications that machine learning is having. One, for instance, is artificial intelligence and machine learning will power the self-driving car, are using all sort of software to recognize faces and are used to interpret and manipulate language. Now, fortunately, in addition to all this pretty dystopian application of machine learning now can be applied into the solution of physical problem. And this is actually what my group has been working on for a few years now. And in particular, I mean, what we have been doing in the last few years is to try to use machine learning based on experimental data to predict known quantities. So for instance, here, this work here that I don't have any time to explain, we took the experimental information about the critical temperature of ferromagnet, and we tried to correlate the chemical composition of a material to its Curie temperature with very good success. Another way where you try to use machine learning models is to try to predict very, very accurate atomistic dynamics. So here, essentially what we do, we train models to compute forces between atoms at the level of an accuracy which is identical to the one of advanced electronic structure methods, which of course are much, much more computationally intensive. And the other aspect we've been working on is to try to solve complex many-body problem. Many-body problems are typically characterized by the fact that they require very large computational resources, and the complexity of the problem scale with the number of atoms. So for problems that contain a very large number of atoms, the methods become, the exact solution become essentially unfeasible. But machine learning, to some degree, can overcome this problem. So what is the project I'm going to offer this year going to be about? The idea is to try to combine two leading theory, one for doing materials modeling, which is density functional theory, and one is machine learning. Density functional theory, in a nutshell, is a very clever way to solve the Schrödinger equation for real materials at relatively modest computational cost. And it is based on two well-established theorems, which essentially says that the knowledge of the electron density is sufficient to determine all the property of a system. Now, this is a very advanced theory that are available a tenth or probably 100 of different pieces of software to solve this particular density functional theory problem, and this generates enormous amount of data. So the idea now is to try to use this data, to harvest this data in machine learning. And the idea is then to combine these two very, very advanced theory into hopefully what can be a new theory that can get the best of both of them. And the idea essentially, there are a lot of problems to construct this link. First of all, we need to find out a very convenient way to represent the quantities that are relevant to density functional theory in a way which is amenable to machine learning. We are going to find, but then if this is possible, we're going to be able probably to speed up enormously the calculation in density functional theory. We're going to probably be able to access new quantity not available in standard electronic structure theory, and hopefully we will be able to construct a numerically exact function, so we will be able to solve exactly without an approximation the density functional theory problem. So this year I'm going to give project along those lines, and if you have any interest or if you just want to hear a little bit more, just please send me an email and we can organize a Zoom call or whatever can be done these days. Thank you and enjoy the rest of.
Hello and welcome to this presentation of the PhD opportunities within the Trinity Ultra Microscopy Group under the supervision of Professor Lewys Jones and myself, Jonathan Peters. Our group's research is based around developing the state-of-the-art in electron microscopy, pushing the current capabilities through designing the next generation of hardware or by extracting new data from existing technology. We are really pushing the limits of precision, speed and sensitivity as required for groundbreaking materials development. We are based in the Advanced Microscopy Laboratory just down the road from the main Trinity campus, where we have dedicated microscopy space with excellent facilities and support, from sample preparation to dedicated staff. One of our main focuses is scanning transmission electron microscopy, or STEM. The foundation of this is that we accelerate a beam of electrons close to the speed of light and into a single point, as small as a few tens of picometers across. We scan this beam across whatever sample we are investigating and collect a range of signals. At its simplest, we use an annular detector, which detects a signal when the electron beam scatters from an atom, or no signal when the beam passes straight through the material. This allows us to image materials all the way down to the atomic resolution, where, for example, we can now see the atoms in a silicon sample. We can even see atoms separated by only 136 picometers. One of the beautiful aspects of this technique is the ability to collect multiple signals simultaneously, such as spectroscopy from X-rays or electron energy loss, giving elemental and bonding information. Because of the power of electron microscopy, it's been fundamental in many aspects of modern materials research, particularly nanotechnology. Advancing these capabilities is where we come in. However, there are two main obstacles we face. First is the cost of the latest equipment. We can easily throw hundreds of thousands, even millions of euro at the problem, but instead we want to be clever and develop ingenious, affordable solutions that will extract the most out of our existing hardware. The second aspect is that our high-speed, high-intensity electron beam can easily damage the material we want to examine, particularly things like organic materials, light materials, such as those used in batteries. In order to look at these materials, we need to use our electron dose efficiently. Some areas we are actively developing include designing better magnetic lenses, electron emitters, or improving electron detection techniques through detector geometry and single electron counting. So this is where the new PhD projects come in. We are looking for students to fill two roles. The first is the application of state-of-the-art microscopy to do really new and exciting materials research. This will involve pushing the limits of our current capabilities to make measurements that were previously thought impossible, whether that be applied to semiconductors, ferroelectrics, 2D materials or others. We have a range of collaborators from within Trinity but also internationally to work with. The second project is for a data scientist to extract the maximum information out of the datasets that we can collect. We now have the capability to collect increasingly large datasets, from conventional 2D images to 3D spectroscopic images, and sometimes even 4 or 5 dimensional datasets. Whilst this data contains much more information, it also requires more advanced processing techniques. Here you can see a few examples, such as using principal component analysis to separate spectroscopic data into signals from different elements, scan distortion correction to achieve the maximum spatial precision from a time series of images, and compressed sensing that is used to reconstruct a full image from undersampled data. As well as new developments, there is also scope to improve existing analysis by making it faster, with the ultimate goal of running it real time as the data is collected, and also making the analysis robust with less human intervention required. This will involve the application and development of modern computer techniques such as machine learning and neural networks. Another area we can improve upon is the simulation of our microscopes. Whilst we would love to say our microscopes are perfect, in reality there are always some imperfections to deal with. For example, our lens systems have hysteresis, and our current method of correcting this is just to wait for the lenses to relax. This is unsophisticated and introduces a massive amount of unnecessary electron dose to the sample. If we can accurately model this hysteresis, we can start developing methods to eliminate or compensate for it. We also need to start accurately modeling things like the energy spread from our electron sources, scan distortion for imaging, and improving simulation of electron to material interactions for things like thermal diffuse scattering. This work will really help guide the development of the whole group's research. So I do hope you have found this presentation useful. Please do get in touch if you're at all interested and we can discuss the projects. Thank you.
Okay, so David McCloskey is my name. I'm the Usher Assistant Professor for the Science of Energy and Energy Systems at Trinity College Dublin, and I run what I call the Nanothermal Research Group out of the School of Physics. This is me. This is a representation of my research group from about this time last year. A few new people on board now. So the areas of research that we are interested in, I would broadly say, are light and heat, and in particular where these two phenomena overlap. So some examples of projects that we're currently funded on are solar photovoltaics and solar thermal heating, where we are looking particularly at the performance of solar PV at high temperatures, and we're coming up with ways for reducing that temperature, and we've shown that we can increase the energy output from solar PV significantly by doing this. So this is currently funded under an SFI project, which is based at spinning out a company for a commercial application. Other things that we're interested in are at smaller scale. So we do a lot of ultra-fast optics with 2D materials, we do plasmonics, we do laser devices with integrated cooling, microfluidic channels and evaporation, stuff like this. And we're currently funded to look at ultra-fast modulators and display technology. Okay, so the first project that I've kind of outlined that I'd like some help with, somebody to do some work on, is related to looking at solar PV performance, particularly at high latitudes. So the price of solar has come down so much now that the people in countries that previously wouldn't have considered it economical are now considering it. So the efficiency of solar panels is anywhere between 15 and 20% depending on the technology you're using, and is roughly independent of irradiance, until when you get down to very low irradiances, it starts to fall off dramatically. And by low irradiance, I mean less than 200 watts per meter squared. Now, if you look at a histogram of available weather irradiance in Ireland, it turns out that for 60% of the time, we are in this region of low irradiance. Now, there are a few tricks that you can do to improve how solar panels perform in this region, and this is what this the gist of this PhD would be. We'll be working both on like a cell level where we put on nanoscale coatings to improve the absorption, but also on a panel level where we change the reflectivity of the glass surface. So that's project 1. Project 2 is related to solar thermal heating, in particular flat plate solar thermal. We're trying to improve its efficiency close to the tube-based one. And this is very important, I think, for decarbonising our energy system in Ireland, because if you look at the sources of energy going into space heating and water heating, you can see that it's almost predominantly done using fossil fuels such as oil, solid fuels, gas, and very little electricity or renewable penetration into heating your house and your water. Whereas solar thermal is a very effective way to do this, and by bringing the cost of this technology down, we're trying to increase its efficiency and increase the efficiency of transferring this heat into the house. Some concepts we're looking at reducing convective heat losses in these plates, and we're looking at designing radiators which work better at lower temperatures, which heat pumps and these kind of solar thermal devices work at. Okay, so if you're interested in looking at the world, finding a problem, coming up with a concept of how to improve or fix that technology, designing it using simulation software, and then actually fabricating it using various nanoscale or macroscale fabrication processes, then testing in a lab and then testing it outdoors, then this is the kind of group or project for you, because this is what we're interested in. So if you're interested in either of these projects, or if you want to propose a similar type of project to us, please send your CV and a short cover letter explaining your interest to my email address before Friday the 2nd of October. These projects do take a little bit of time. You're going to have to write the majority of it yourself. I'll give you some input, so do contact me as soon as possible.
Hello everyone, this is John Donegan. I'm the Professor of Physics and Applications of Light in Trinity College, and I'm going to outline a project I'm suggesting for the IRC application. So it's termed soliton spectroscopy and dynamics in aluminum nitride and lithium niobate micro-resonators. So a soliton is a very particular individual type of wave that maintains its shape even if it propagates in time or in space. And solitons are caused when there is a cancellation of nonlinear and dispersive effects. Nonlinear optical effects generally occur at high optical powers, so again you need structures in which you can generate these high optical powers, generate the nonlinear effects, and then have them cancelled by the dispersive effects in the medium. So we do that in a system of a micro-resonator, as shown here. This is the case of an aluminum nitride ring resonator. The light enters into this waveguide as here, and then is coupled into the ring. Now this is the region here where you can see the coupling very clearly between the two of them. This is the input waveguide, and then we get coupling across into the ring resonator. And the light then can traverse round the ring many times as it does so, and eventually some of it also exits and leaves the waveguide again on the output side. So if we now look at the transmission of light through the system, this is what we find. So again, we are measuring in this wavelength range. This is in the near infrared, close to the region where optical fiber has its lowest loss. At a low optical power of 40 microwatts, this is what we see. We see a series of dips, and this corresponds to the positions where light is coupled effectively into the ring resonator. In other cases, light is not coupled here very strongly indeed in this situation. So these resonances are determined by whatever material and geometry that are there, but effectively where an integral number of the wavelengths fit into the ring radius, you get these transmission dips. Now, if you increase the power from these into the ring resonators, then on the output side, suddenly, instead of dips, you actually see emission. Here's a series of lines from this system, and again, a series of lines that are equally spaced is actually called a comb, remind you of a hair comb. And all sorts of different arrangements can be generated. This one is called a chaotic one, where the lines are not so equally spaced. And then at the top here, we have a very beautiful representation of what's termed a soliton crystal. Well, you can see again, a large number of lines are generated, and they are roughly 5 of what's called these free spectral range apart. An even more extraordinary and beautiful creation is the soliton itself. So this extraordinary spectrum, as shown here, is a series of hundreds of individual lines which are generated from that ring resonator. So let me explain quickly what's happening. Here's the pump wavelength coming in our waveguide. Generates the resonances, all these comb lines, as from the previous arrangement that was there. And when we balance carefully the dispersive and the nonlinear effects, then we generate what's called a soliton. And in this situation, generates a very short pulse of light on the order here of about 66 femtoseconds. Imagine that extraordinary behavior from such a tiny, tiny resonator. A particular aspect of solitons is that they are a quiet or a low noise state. And in fact, if you look at a photodiode, which takes the optical power from all of this, you can barely distinguish what you see from the photodiode when there's no light on it than when all of these lines are present on it, indicating again this very low noise state. In fact, in this system, you can generate not just infrared light, this is all infrared frequencies, but in this image here, you can actually generate green light, and there's red light generated, not quite so strong to your eye from this. So these harmonic generation effects are also present in the system. So again, extraordinary behavior is possible from just a simple ring resonator. So for the IRC application, solitons themselves are key in the development of a new optical frequency reference, a reference that has an uncertainty in just 1 part in 10 to the minus 15, quite extraordinary level of precision for the frequency of the light. We're going to do this by developing solitons in aluminum nitride resonators and lithium niobate. That's a different material. Particularly, you can electrically tune it, and that's why it's interesting. So to really make this happen, we have to use important fabrication techniques, including electron beam lithography. The system is modeled by the nonlinear Schrödinger equation, and again, that's an important part of what has to be done here is the modeling and the experimental work working together. And in turn, we will also use laser systems that my group has developed over many years in the hope of generating again all of these lines from the UV to the visible to the near infrared. Now, as you know, I probably haven't explained, the IRC is a very competitive application process, so students must have a first honours result from their third year. And if you want to talk about this more, please contact me as follows, jdonegan@tcd.ie. And thank you very much indeed for your time.
Okay, welcome here. I'm going to tell you a little bit about this project called Imaging Without Microscopy, the Quantum Sudoku. I'm sure you know what a Sudoku is, but I'm showing you a picture on the right anyway. And on the left you have a picture of myself in case you're from outside and you don't know who I am. So I give a face to the name. I'm a professor here in the School of Physics, and I'm a theorist, which means that this project is actually a theory project. So let me start by telling you very briefly about a publication of mine that appeared just a month or so ago. It's called Disordered Information from Conductance, a Quantum Inverse Problem. Let me tell you what this publication is about. Here on the right, you have on the top an image of a graphene nanoribbon. Actually, even though I'm going to talk about graphene here, there's nothing exclusive about graphene. This can be used with any material, as a matter of fact. But here I have a graphene nanoribbon with a number of impurities there. Okay, so if I know the sizes of my device or my system, and I know how many impurities I have and where exactly they are located, I can very easily go down, go to the lower graph here, down this arrow labeled D on the left, which is a direct calculation, which leads me to the transmission coefficient, or if you like, the conductance as a function of the energy here. And then on the left, I have a green tick mark that kind of illustrates or demonstrates the ease with which we can do that. Indeed, it's a very easy task. Now, the question I want to pose is this. If we were to do that in reverse, i.e. if I give you this seemingly noisy conductance, right, and then I ask you, can you tell me how many impurities I have and where they are, etc. So the inverse problem, which you have this this arrow labeled I on the right, there's a red cross there indicating that, well, this is not so easy. It's actually quite a tricky problem. But what this paper does, this article does, we reports an inversion tool that we developed that pays. Oops, sorry about that. Sorry, just go back to this inversion tool that we developed that extracts detailed information about this device, about the scatterers, impurities, defects, etc., of a two-terminal quantum device by looking at these seemingly noisy conductors. So we start from this bottom graph, and we are actually able to tell precise information about these scatterers. Okay, so in particular, we can tell the number of impurities with great precision. So the question is, I'm sure you're dying to ask me, is that what does that have to do with the Sudoku problem? Okay, now imagine that this same graphene sheet is deposited on electrodes that are electrode lines numbered here in red and blue, right? And they are like forming this grid. Okay, so as a matter of fact, because these are electrodes, I can inject current and extract current from any electrodes. So I could, for example, interrogate this system with between electrodes 2 and 3 and get or measure or find the conductance between them. And as a matter of fact, I can actually do that with any pair of electrodes. And I want to draw your attention that once I have that, I can then use the inversion tool that I told you about. And the inversion spits out here on the bottom this black number that gives the number of impurities contained in between these electrodes in question. And I want you to see that I can do that with any pair of electrodes, right? And in fact, I can do that with any pair. In fact, I can interrogate these in any way I want. So I can populate these with these integers here, which corresponds to the number of impurities lying along a certain row or a certain column. And I want you to see that they are absolutely identical. So the predicted number coming out of the inversion coincides with the exact number of impurities that you find there. So, of course, if I now ask you, if I now try to find what or how many impurities there are in one sector here of this device, well, now you can see where the resemblance to the Sudoku problem is, because then it will be a matter of finding out the number that satisfies the constraint given by these black numbers produced by the inversion tool. So these, of course, is a way to map the spatial distribution of impurities, right? But we can do that without using microscopy. We could just interrogate the system with these grid-like electrodes, and we can do the inversion and find exactly where they are. Now, if to summarize, this Sudoku-style inversion tool provides spatial mapping of impurities, defects, scatterers, you name it, in a quantum device, and there is no need for microscopy here, which is a pretty interesting thing. Just to reiterate that there's nothing exclusive about graphene. Of course, besides the electronic conductance, this inversion tool also works with thermal, magnetic, and optical conductances. So we can actually use these properties as well, which would open up a whole range of possibilities in terms of alternative imaging strategies. Now, this project requires candidates with a solid mathematical and computational background. If you are interested in one and you want more information about this, please contact me here. Of course, you understand that I was not able to provide too much information here, too much details, but feel free to contact me if you want to find out a bit more about it.
Hi, welcome to everyone back to Trinity for the final year. So many of you remember me from first year. My name is Louise Bradley and I lead the nanophotonics group here in Trinity. I want to tell you a bit about firstly the group and then the specific project which I would like to apply to the IRC for. So my group specialises in the generation, manipulation and detection of light on the nanoscale. We're funded by lots of different funding agencies, including Science Foundation Ireland, the Irish Research Council. We also have Marie Curie funded postdocs in the group, and we have PhD positions funded by Amber, by IPIC, which is the Photonics Centre in Cork, and we also have received funding from Tyndall, which is a national access programme. So this is the current group. There are 3 postdocs and 7 postgrad students in the group at the moment. The project that I want to tell you a bit about today is based on novel optical sensors with 3D printed responsive polymers. This project will be in collaboration with Professor Larissa Florea from the School of Chemistry. So Larissa specialises in the development of the responsive polymers, and they can be printed into any type of 3D structure using the nanoscribe tool, which is down in the Advanced Manufacturing Laboratory of Pearse Street, and it's based on the process of 2-photon polymerization. So what we want to do in this project is to take the materials which have been developed and to understand and quantify the changes in the structures which we make using the nanoscribe, and also to understand the changes in the refractive index when these responsive materials are exposed to different kinds of stimuli, whether those stimuli are liquid or gas. And then based on this knowledge, we want to be able to design and to fabricate and ultimately to test structures which have been optimized for a range of sensing applications. So I'm going to give you an example. So here you can see a checkerboard type structure. So the micrographs there taken with the scanning electron microscope show that we have one structure which has got a period of over a micron and the other one which has a period of about 500 nanometers. So when we look at the different structures in the transmission spectroscopy, you can see that they correspond to very different colours. Now, if we expose this structure to IPA vapour in a closed cuvette and we monitor what happens as a function of time, we can see that there is a distinct colour change arising as the IPA becomes more concentrated in its gaseous form. So if you look across the top, we can see that the top square goes from a greeny yellow colour to a more progressively blue colour, then to a reddish orange colour, and then it starts to fade towards a lighter bluish colour. And across the bottom also we can see distinctive changes in colour going from green to a very dark blue to a reddish orange and back then to a light blue. This is completely reversible and the response will be different for different kinds of gases and liquids. So for example, here you can see the spectra that we take in transmission, and we can monitor these spectral changes as a function of time. So what we want to do in the project is to explore a range of possible polymers, and we have free design of our structure. So we want to quantify, design, optimize and test for different applications, considering both gases and liquids. We'll do a series of measurements which include dynamic spectral measurements, angle result measurements, as well as using a range of techniques to probe the structural changes within our materials. And from this we hope to develop a series of structures which will be able to be used as colour monitors or even spectral monitors with a wide dynamic range. There are other funded positions available in the group as well. They're on the topic of plasmonics. If you're interested in finding out more about those, please contact me directly. Thank you for your attention.
So, hi everyone. In this short talk, I'm just going to describe the PhD project I'm offering this year. So the broad title is The Ever-Changing Universe, Exploding Stars and Catastrophic Collisions. And so my research focuses on understanding some of the most energetic explosions in the universe. So we do this by looking at supernovae. So these are the explosions of stars at the ends of their lives, and these can massively outshine their host galaxies, as is shown here. So these are very energetic explosions. And then I'm also interested in are actively involved in the new field of the follow-up of gravitational wave detections. So this involves the collisions of neutron stars that now with the LIGO Virgo experiment and then electromagnetic follow-up that we can see and hear. So some of the big questions that we want to answer are, how do normal type 1a supernovae explode? Can we explain the extremes of stellar explosions? There are a lot of weird things out there. How do they explode? And this is really testing the boundaries of explosion models. And then what is the diversity of neutron star mergers? So starting with type 1a supernovae, so these are the explosions of small dense stars called white dwarfs at the end of their lives. They're the main producers of iron in the universe. So any iron on Earth was produced most likely produced in a type 1a supernova explosion. They're also critical in the discovery of dark energy, so in understanding the cosmology of our universe. And so we now know from studies of supernovae and the cosmic microwave background that dark energy makes up approximately 68% of the mass energy of the universe. Dark matter, about 27%, and then the ordinary matter that we see around us, like people, the Earth, galaxies, this only makes up 5%. So type 1a supernovae are essential for understanding cosmology and the makeup of the universe, but the key problem we have is that we don't actually understand how they blow up. We just use empirical relations to use them for cosmology. We want to be able to do better than this. So there are two leading mechanisms for how a type 1a supernova explodes. One, as shown here, is the case where you have a non-degenerate companion star, so some kind of main sequence star or red giant that is onto which a white dwarf is accreting matter. And this causes it to approach the Chandrasekhar mass limit, which triggers a runaway thermonuclear explosion. And this completely destroys the star. In the other case, you can have the merger in a number of different ways of two white dwarfs. So in this case, you can see in the video here, two white dwarfs merge, and this can also produce an explosion that for some models is consistent with a type 1a supernova. So one of the key questions we want to try and answer is which of these scenarios is producing type 1a supernovae, and it looks like it potentially could be both. The other key question, as I said, that I'm interested in is understanding neutron star mergers. And the key astrophysical question that we can answer with this is, where are our process elements produced? So these are elements heavier than iron in the periodic table. And it's a long-standing question in astrophysics, whether they're produced in core collapse supernovae, as you can see on the left, or in neutron star mergers, as you can see in the video on the right. It's only been possible with the recent, detection 3 years ago of 2017 GFO that was detected in gravitational waves, and then subsequently in electromagnetic observations. And from this, we were able to predict or show that it was more than likely that this was producing gold. So you can see here the light R process and the heavy R process elements, and you can see where gold sits in atomic mass number. And so, yeah, the key question we want to answer is try and find more of these using the upcoming LIGO Virgo advanced runs and figure out where is the origin of gold and how much is being produced. So how do we go about answering all these questions? We use telescopes. So I'm involved in a number of surveys, the Zwicky Transient Factory, Black Gem, and then also other search facilities. So we search for things, do rapid multi-wavelength follow-up. This is quite an active field that's changing all the time. We also do theoretical modeling in the group if you're interested in that. So this just shows some explosion models on the left and then some spectral fitting on the right that we did to show the R process elements in this first kilonova event. And then we also ask the question, the questions that I've been saying about what stellar systems produce type 1a supernovae is all gold made in neutron star collisions. So if you're interested in any of these topics, please get in touch with me. You can send me an email. It's kate.maguire@tcd.ie, or you can find my information on the physics web pages. I look forward to hearing from you.
Okay, so hi everyone. My name is Neale Gibson. I'm an astronomer here at Trinity, and I'm going to tell you about a couple of PhD projects we have in the field of exoplanet atmospheres. So as you probably know, thousands of exoplanets have been discovered since the 90s. So exoplanets are just planets that orbit stars other than our sun. And this is just a plot of the planet mass versus orbital separation, just a way to represent the exoplanet population. And I've overplotted the position of Saturn, Jupiter, and Earth, and so on here. And one of the key things is that the planets are much, much more diverse than what we see in our own solar system. The problem is we don't really know that much about them beyond simple physical measurements like their masses, radii, orbital properties, and so on. So the goal of my work is really to find ways of understanding these planets in much more detail. And to do this, we need to get spectroscopy of their atmospheres. So the key to doing all this is something called planetary transits. So many of you will know a planetary transit is just when a planet passes in front of its host star. And if you measure the brightness of the star as a function of time, you'll see this characteristic dip. And it's just because the planet blocks a certain portion of the light from the star. And we can use this to not only detect the planet, but also to measure the mass of the planet as well. And transits don't just occur in exoplanet systems, they also occur in our own solar system. And this is just a really beautiful picture of the sun. You can see sunspots and so on, and you can see Venus transiting the sun. And what I want to bring to your attention is that if you zoom in on Venus during one of these transits, you actually see this very thin annulus of light. And essentially this is light that filters through the upper atmosphere of the planet. And if we can get access to this, the light that filters through the atmosphere, we can learn a lot about the atmosphere itself. And this is a technique called transmission spectroscopy. It works for exoplanets as well as solar system objects. And if we can get access to this, we can learn lots of cool things like the composition of the planet, the chemistry, scattering properties, temperature structure, and so on, things about dynamics. And long term, we're hoping to use these techniques to find things like biomarkers. So in other words, signs of life. So maybe oxygen in an Earth-like planet, for example. So there are two primary techniques to do this. One is just to take a series of transit observations. So these are just, again, the brightness of a star as a function of time. We do this at multiple wavelengths, and we measure the transit depth as a function of wavelength, and we get the effective radius of the planet that we can just convert directly into a spectrum. So I'll not go into a lot of detail here, but we can use this to directly observe the spectrum and then learn some information about the planet. So in this case, we get some sort of scattering signature, which indicates clouds, hazes, or so on in the planet. So another thing we can do is to observe high resolution spectroscopic observations. So again, I'm not going to go into a lot of detail, but similar to the radial velocity method that we use to detect exoplanets, so we measure the Doppler shift of the star as it orbits the common center of mass, we can use the much larger Doppler shift of the planet to actually disentangle the planet spectrum from the stellar spectrum. And we do some data processing, and we end up with a plot like this. So this is essentially you're separating your signal in velocity space. So this is the velocity amplitude of the planet versus the velocity of the whole system. And if you see a spot in the right position, you can use this to detect atmospheric features. And this is what we're hoping to do in the future, to detect things like, as I say, oxygen and Earth-like planets. So what is the project itself? It's essentially to investigate and learn these two techniques. So essentially to observe time series spectra of star-planet systems. And we use some of the world's most advanced telescopes, such as the Very Large Telescope at Paranal, which you may have an opportunity to visit at some point, and also things like the Hubble Space Telescope. And we take these observations, and then most of our time is spent trying to disentangle these tiny signals from the exoplanet atmosphere from the host stars. So we use a lot of sort of advanced statistical techniques to do this, to try and disentangle these signals. Once we've done this, we then model planetary atmospheres in order to interpret the data. And of course, we want to prepare for things that are coming in the future. So there's a couple of really interesting facilities coming online in the next few years, which are really well timed for these projects. One is the European ELT, which is going to be the world's biggest telescope. It's going to have a 36-meter diameter, and it's going to be amazing for starting to look at terrestrial planet atmospheres. We also have the James Webb Space Telescope, which is hopefully going to launch next year, and it's hopefully going to do some great things too. So if you're interested in astrophysical observations, atmospheric physics, exoplanet detection, characterization, stats, and machine learning, then give me a shout and I'll tell you some more about the project. So thanks a lot.
Hi everybody, my name is David O'Regan and I'm going to speak to you for a few minutes about the work that we're doing at present in the area of quantum materials theory, and a project that I think would be quite interesting to develop an IRC proposal on building certain quantum mechanical exact conditions into the simulation of materials for renewable energy processes. So these could be solar cell materials, for example. They could be battery materials, or they could be materials for catalysis for conversion of CO2 into liquid fuel. Okay, so we're actually pretty diverse in my group in our interests, and we can develop projects on different types of topics, all the way from quite theoretical up to really an applied project in collaboration with experimentalists. So to discuss the types of options that we have in materials theory in general, just pop me an email, it's no problem. Okay, we're a group of, myself, 3 PhD students at present, one postdoc being hired at present, and one up the sleeve. So we're a mid-sized group. And broadly speaking, where our interests lie is in broadening the scope and the relevance of quantum mechanical simulation of materials. And this involves sometimes developing new pen and paper theory to make the simulations more accurate. Depending on the student's interest, we can do quite a lot of software development. We try and make that modular and user-friendly. And then, some students prefer to just take the software off the shelf and really get to grips with the physical problem. So we do respond quite a lot really to real-world requirements and needs. We interact with industry and experimental colleagues quite a lot. And this takes us really right across the material world. So we've looked at oxides in the past. So these are the types used in certain types of solar cells, even semiconductor whole devices. So these are single photon emitting quantum dots of relevance to quantum computing, even up to very complicated systems like metalloproteins in the human body. This is myoglobin, so we're into quantum biology there. And we looked at nanoscale properties. These are mechanical properties of different metals in adhesion at the nanoscale. We look at photonics and plasmonics, so that this indicates the response of different metal alloys to laser light. And we also do even classical modeling. So this is some modeling we've done a couple of years ago to try and predict really the size and morphology that different types of two-dimensional material like to adopt. So we're pretty diverse in our interests really, and we're able to incorporate the needs and interests of different types of students. But broadly speaking, we're doing quantum mechanics, and we're using a formalism of quantum mechanics known as density functional theory. And I like to think of density functional theory as the biggest thing that no one ever heard of. So it's one of the most influential ideas in science, I think, in the last 100 years, but it somehow doesn't make it into our undergraduate courses. This is a bibliometric study from nearly 10 years ago, showing that at that time, something like 18 out of the top 22 physics papers or papers in American Physical Society journals were about density functional theory, and how to make this quantum mechanical theory into a practical method for simulating materials. The runners-up, the other papers, are little old things like the theory of superconductivity, the BCS theory. Now, I jest a little bit. I mean, density functional theory is if you want, a necessary evil in some ways. It's the only practical way that you can use quantum mechanics to explain and predict the properties of real-world materials on moderately sized computers, the sorts of computers that most research groups have available. So it's very, very influential. But actually for real quantum materials, for materials that are really of most interest for carbon sequestration, for photovoltaics, for very high performance magnets, these are materials. There's quantum materials for which quantum mechanics is responsible for the key properties of interest, actually, it's the multi-reference, if you like, Schrodinger's cat effects that makes density functional theory perform very poorly. And that's where we come in my research group. So if we look at manganese monoxide, which is a very challenging system, it's not unlike the pairing materials for high temperature, certain high temperature superconductors. Standard density functional theory gives you absolute garbage basically for the band gap. So it gives you a large spread of results depending on which version of density functional theory you use, and they all underestimate the band gap with respect to the experimental band gap, which is down here around 4 electron volts. You can use a very expensive version of density functional theory. You push up the average value, but you still have a big spread. And you can even go beyond density functional theory to Green's function-based methods that are getting very, very expensive, and still you do quite a poor job. So this is where we come in my research group. What we've been developing for the last few years are these methods to, on a case-by-case basis, measure the error in density functional theory. We measure the strength of its breach of certain known quantum mechanical exact conditions, and by hand, really with sort of cheeky pen and paper tricks and code hacks, we put the right physics back into density functional theory. I mean, there's a lot of technical detail under the bonnet, and it's actually quite a rigorous thing, but this is where we are in practice. We can get just from this system, and I have many other examples like this. I just show you one. Good agreement with experiment. So this is an area that I think is taking off, and we have been looking at kind of very canonical test cases that are hard for density functional theory up to now. But I really want to push this forward now into the realm of materials that are cutting edge, and particularly I'd like to take this theory, which is developed to be energy efficient on supercomputers, and actually use the theory to try and discover, explain, and develop new materials for energy applications. Okay, so the idea is you have a self-correcting density functional theory that's self-contained, transferable from one material to another, accurate, efficient, easy for people to use, and really to disseminate this methodology in as many DFT codes as we can reach or we see relevant, and to apply these and to make interface with experiment where it's most relevant in the energy realm. So we could look at, for example, phase diagrams of high-performance battery materials. There are certain new categories of photovoltaic materials and transparent conducting oxides for solar cell applications, or there are things like zeolites for capturing and catalyzing toxic gases or gases like carbon dioxide. I mean, I'd be very interested in actually combining some of the methodology that we've been developing in a hybrid theory experiment project, for example. But there are different types of projects that we can develop and really tailor to the individual interest of the students. So some students would just prefer the theory. They actually like doing applied quantum mechanics, pen and paper exercises. Some students love software engineering, so they love coding, they love high performance software. And some students just want to become the expert on a particular class of material and drive the physics and the chemical physics forward there. And some people find it very, very stimulating to interact and even participate in experimental work. So I think there's a full range there that we could think of developing an IRC project on, and I would be willing, I think, to support one or two applicants this year. Much more than that, and I think one spreads a little thin. So I'm very, very happy to be contacted. You have my email address here, david.o.regan@tcd, and I look forward to hearing from you. Thank you very much.
Hello, I'm Michael Coey, and this short video will let you see some of the things that are going on in our magnetism and spin electronics group. As you can see from last year's photo, which was taken pre-COVID, we're one of the bigger research groups in physics, and every year we take on 2 or 3 new PhD students. Magnetism is a really exciting subject. It underpins the information and big data revolutions, and new things are being discovered all the time. There's been a Nobel Prize for magnetism roughly once every 10 years. Our labs are split between SNIAMS and CRAN, and we'll have a peep into each one. At the end, Plamen will tell you about the new PhD topics. But here we are in Sniams, and Lucy will take over for this part of the tour.
Hi, I'm Lucy, a second-year PhD student in the group, and I'm just going to show you around our lab in the Sniam. So in this lab, we make materials in bulk and thin film form. Here you can see Hassam making alloys using the arc melter. So he's melting the metals by means of an electric arc to form alloys with a particular composition. But we can also prepare thin films in the Sniam, and we do this using pulsed laser deposition. With this technique, we strike a target with a laser which vaporizes the target material and forms a plasma plume. The material then deposits onto a substrate, resulting in the growth of a thin film. So at the moment, I'm using this to grow metal oxide films. After preparing our samples, we need to magnetically characterize them, and the Sniam is the home of our very own SQUID magnetometer. So SQUID is a strange name, but it stands for Superconducting Quantum Interference Device, and it allows us to apply a magnetic field to a sample and measure the resulting magnetic moment. We can scan fields of up to 5 Tesla. We can also vary the temperature from 4 Kelvin up to about 400 Kelvin. But if we want to measure the magnetization at higher temperatures, we need to use our VSM, or Vibrating Sample Magnetometer, which is being fixed up at the minute. So Shceme, another PhD student in our group, is working on this. Here you can see him designing some parts on SolidWorks, which he then printed using our very own 3D printer. It's extremely convenient to be able to print anything you need, really. People in our group have been using it frequently since we got it in the last year. There are also members of our group studying the effects of magnetic fields on liquids. So Shruti here is using some new equipment to measure sessile and pendant drops in order to determine the surface tension of different liquid samples. So now I'll hand you back to Mike, who will take you through CRAN for a little tour of what we can do in our lab over there.
Now we move over to CRAN, where we have state-of-the-art facilities for nanoscience research. It's here we do most of our thin film growth and patterning in the clean room to make devices, and we also make all of our electrical and optical measurements over here. Most samples we need are thin films or complex thin film stacks. This one is a tunnel junction sensor. And we're really lucky to have the new €3 million TEDdy facility, where we can make near-perfect devices by sputtering in ultra-high vacuum. The tool also includes chambers for in-situ study of the films just after we produce them. They must be thoroughly characterized by X-ray diffraction, microscopy to see if there are any magnetic domains, and then by SQUID magnetometry over in Sniams. Next, we pattern them lithographically into the shapes we need for detailed electrical measurements, which we make with different directions of field and current, and also different temperatures. Sometimes we need to see harmonic response to AC excitation. Here, Simone and Zhang are making measurements on a new 10 nanometer thick amorphous film of dysprosium cobalt at temperatures from 5 to 300 K in a magnetic field of up to 5 Tesla. It's produced in the bore of the big green superconducting magnet, where no liquid helium is needed. But some of our most original data comes from ultra-fast optical measurements in the photonics lab, and Chandrama will now give you a little tour.
Welcome to the Photonics Laboratory in CRAN. This lab is dedicated to several state-of-the-art ultra-fast high-energy laser systems. Using optical tools, these laser pulses are fired on the sample under study. As we are interested in magnetic systems, our main area of research is ultra-fast non-equilibrium magnetization dynamics, which are as fast as sub-picosecond in time scale.
And now Plamen will briefly run through some proposed project ideas for any new PhD students that want to join our magnetism family.
Hello, I'm Plamen Stefano, and I'd like to present to you 3 selected topics that are available for you this year. The first one has to do with creating a magnetic neural network, the weights of the synapses of which we can adjust rather rapidly and effectively infinite number of times. The second has to do with applying amorphous ferromagnetic materials into relatively complicated magnetic stacks which aim to achieve non-volatile logic functionality on chip. The third has to do with trying to revolutionize how we switch optical data transfer and modern optic fiber networks by magnetic means. Last, I'll just want to leave you with a couple of ideas for titles for projects that we could also support in the course of the next few months. Below you can see the contact emails.
Hello, welcome to my talk for an IRC postgrad project. So the topic in general is light at night and light pollution. So why is light at night important? Well, it tracks human occupation and its activity. So the image at the right, for instance, shows the two Koreas. North Korea, quite dark. South Korea, relatively bright. A lot more activity. Look at the sea as well. There's light from squid fishing boats, where they used to attract the squid. So where humans are located is traced in the lights, and we can use this to track lights and activity night on night. But the other side of this is that the light we see when we look down from space also indicates an energy loss. And the energy being used for lighting and light pollution is increasing at 2% annually. It's driven by our 24/7 culture and the increases in both population, the growth of light into the into the environment, and also development in the economy. So all of this has an obvious energy cost, but also monetary and environmental cost, and at high levels can actually affect human health. The image to the right, in the town of Bath in the UK, images taken several decades apart, we can see quite a dark area in the top image, something we'd regard as quite dark by modern standards. In the bottom, a lot more light. So although light can be a lot more controlled nowadays, we're using it a lot more frequently. Buildings are illuminated. We can even see light shooting off into space in the building on the right. The bottom picture shows an image taken from Killiney Hill looking back over the city, Comet Neowise, recently, and you can see the amount of light acts to damage the astronomical environment. So all of this requires that we quantify the light emitted and to understand its origin, how it propagates out into space, but also how it propagates out more widely into surrounding countryside, and all the costs associated with this. And if we come up with a quantifiable prediction, we can use this for modeling, forward modeling, and predicting where the likely changes in light is going to occur, what we can do about it, and that can inform policy and planning. In the Republic, the image at the top right shows areas where light has been increasing from 1995 to 2010, and we can see it's increased in the red color. Blue color indicates decrease, and white indicates no change. So the white is basically areas which can't be built on. The graph shows the measurements taken from space. We see a 10 times faster growth in the Republic, and this increase in light then means that we're having a much more big impact on the environment. And the bottom picture shows an image taken from Wales, 120 kilometers away. In terms of the public aspects, we've got nearly 500,000 lights, quite a large amount of lighting, but there's also a commercial component, as indicated in the reaction to the Celtic Tiger, the growth, and also new lighting, new more efficient lighting and cheaper to use can actually lead to an increase in light because it's used more frequently. So the image at the bottom shows the change in the center of Milan as white lighting from LEDs were introduced. So we need to quantify these developments and model them. The image here, we show Dublin taken from the space station. We can see the different types of light. Blue is new LED lighting. We can compare that with the public lighting and come up with a model for can we calibrate that? Can we predict what the light should be emitted and what we detect from space? And over nearly 2 orders of magnitude, that's what I see in the sample areas. This work done by final year project student and myself. So we can map to these local sites and develop a calibration and then compare that with the ground energy use and derive the corrections. But we need to actually understand obscuration and scattering and effects as well. Luckily for Dublin, we have a very good LiDAR model, a laser altimeter model. We can actually model the locations of buildings, their heights and so on. And then we can use the model then to predict how much light is going out into the environment. We can quantify these in different directions, different types of light, different colors of light. Trinity is one of the few areas working in this field. It's getting a bit of a reputation internationally. We have high resolution satellite imagery. We can look at the effect, important topic now, the effect of the economy in light, COVID-19 effects, correlation with activity, and as you can read there, land use, commercial, retail. We want to strip that off and understand these various components. So we can use radiative transfer models to understand and compare our results with international cities, as well as supply recommendations for the government at different levels. If you're interested, please contact me at brian.espey@tcd.ie. Thank you.
So I'm Paul Eastham, and I do, as you can see from these slides, theory of quantum light and matter. So I guess the question is why you might want to join my group. Well, I think the main reason is you want to do theoretical physics. And I might just say, I don't think that's just an activity for the TP students. As far as I'm concerned, it's something you can do irrespective of your speciality at this stage. I mean, I have a physics degree. So, what is the qualification? Well, I think the qualification for being a theorist is, do you want to make theories? That's what we do. And in my case, those theories are mostly equations, like those of quantum field theory, that we study with pencil and paper methods, and sometimes computational methods. So if that's the sort of work that appeals to you, making theories of your own, you might want to work with us. So what are these theories? These are theories based on quantum mechanics of fundamental particles of light and matter, electrons and photons, and we look at how they behave, particularly in small structures like semiconductor nanodevices. And which all sounds a bit abstract and far removed from reality, but it's not. We work quite close to experiments and sometimes directly with experimentalists. Particularly, we try and make sure there's always some path for our theories to be tested in the lab. It's often quite hard, as you might imagine, to persuade an experimentalist to do something that a theorist has kind of dreamed up in the lab, in the office, but you can do it, and we do it. So if you're interested in doing theoretical physics that has contact with kind of experimental reality, and maybe would like to see your theories turned into a real experiment, that might also be some kind of reason to think about working with us. So on the slides here you can see, because an old photo of the group, we're a bit bigger than that now, but not so much, and some pictures from one of our recent discoveries, and so a kind of general thing about what we do. We're interested in the quantum physics of light and matter, photons, electrons, and the cool stuff is, well, that's already quite weird, and the way understanding those things, the way those things behave, and understanding that, and once you do understand it, you can figure out how to change it, and you can make it do things which it doesn't normally do, things which are interesting, things which can be useful for making new devices and things like that. So we basically are trying to discover new ways for light and matter to behave, and we do that by making new theories, often kind of forms of quantum field theory, although that's kind of a bit of a fancy term that we don't really need. We study these theories and we propose new devices, new experiments, new ways to produce interesting effects. So that brings me on to what you might do and areas we're interested in. We work on quite a lot of areas, but two kind of possible areas where I'm keen to get students in. The first one is related to a discovery actually on the slide before. A few years ago now, we discovered that photons, particles of light, can have a half integer angular momentum, and an angular momentum which is half the multiple of Planck's constant. And hopefully we've taught you enough physics by this point to know that that's rather weird, because normally you have bosons with integer multiples of Planck's constant and fermions with half integer multiples of Planck's constant, and you get light photons are bosons, so you shouldn't get a whole multiple of Planck's constant for their angular momentum. In fact, we found that there is a sense, a kind of very real sense, in which they do have a half integer angular momentum. Now, we haven't actually built on that very much since. Other people have. They've done interesting things like show that you could have any fractional angular momentum for light. But one of the things I'd like to do now is come back to that work and look at whether we can make optical models of other properties of fermions, in particular things like the exclusion principle. You might say, okay, it's half integer angular momentum, it's really some kind of fermion. But actually it's not, it's just the half integer angular momentum. If you want to bring in these other aspects of fermionic behavior and see these kind of effects for light, you need to bring in some new physics. So I'm interested there in whether we can do that, and actually more specifically whether you can design photonic circuits that realize unconventional properties for light, like analogues of the exclusion principle. The other area I'm interested in, which is more practical, this is an area we've been developing a lot in the group recently, is looking at how heat flows work at the quantum level. This is probably a deep perversion of mine, because I always thought that the most interesting bits of physics as an undergraduate were quantum mechanics and thermodynamics, and now I've discovered that there's an emerging discipline looking at how these things combine and what things like heat means in quantum systems. And we've been doing some quite practical things on this, looking at heat flows in things like semiconductor quantum dots and how you can control those heat flows. So we're interested really there in looking at how we can control heat flows at the quantum level, and particularly how we can do that to do useful things, maybe for quantum technologies. So if these are the sort of things you're interested in, I'd be very happy to talk to you about potential projects and IRC applications. Just drop me a line by email to the address below. Thank you.
Quantum dynamics of nanostructures. This is a theoretical and computational project which will be carried out in the quantum transport and spectroscopy group. This is a new group which was established this year in the School of Physics. There are currently 2 members. I am Andrea Droghetti and I am the group leader. Then we have a postdoc, Anita Holder. We are funded by the Royal Society and Science Foundation Ireland, and we work in collaboration with the computational spintronics group of Professor Sanvito. So we study the properties of materials at the most basic quantum level. So we are interested in a wide range of systems, from magnetic materials to nanostructures of 2D materials, to nanodevices such as molecular junctions, and even biomolecules like DNA. And once we know the atoms we have in our system, we brute solve the Schrödinger equation using only a few approximations. This cannot be done analytically, of course, so we code software that then are used to carry out numerical simulations of supercomputers, such as those managed by TCD Research IT or the Irish Centre for High-End Computing. So, of course, the goals are, first of all, to understand the basic properties of materials, but also we want to predict novel properties which may be useful for a wide range of applications in nanoelectronics or biosensing and so on. So the proposed project here consists in looking at light-matter interaction in materials. So we will not study model system, we will look in real molecules, real solids, real devices, and try to understand the fundamental physics of light-matter interaction, but also we will also understand whether we can induce new states of matters by using light. We will also address the electron and spin dynamics induced by light. We will look at energy conversion processes, and we will understand whether we can use light to write and read information. So in general, we will consider a quantum system in its ground state. Then in our simulations, we will turn on an electromagnetic field, a Raser field, if you like, that will excite our system, or if you like, it will pump our system in a non-equilibrium state. Then we will follow the real-time dynamics. And we'll try to correlate the quantum dynamics with the macroscopic behavior of the system. In particular, we will be looking at time scale, which is really short. It's femtosecond, 10 to minus 15 seconds. And this is the time scale of electron motions. And there's literally is very, very little known about the physics such as short time scale. This is because theoretically it's challenging, while from an experimental point of view, it's harder to find experimental techniques that have such a short time resolution. So, I mean, with this project, we are really entering into we are really trying to address new physics. So only recently there has been some new experimental techniques that enable the study of electron motion at this characteristic time scale. These experimental techniques are in general called pan-probe spectroscopy. And we've been working with one of the world-leading group in spectroscopy. This is the group of Professor Mirko Cinquetti at the University of Dortmund in Germany. So we'll compare the result of our theory with the experimental result by Professor Cinquetti. So just to give you an idea of the type of systems we may be interested in, let's consider something you might have heard about, which is a solar cell. We have a material which is in between two electrodes. Then we shine light. This will create electron-hole pairs. Eventually, these electron-hole pairs will split. Electrons will go into one electrode. Holes will go into the other electrode, and this will generate an electrical current. So in this project, we may be able to tackle this very complex physics from the basic principle of quantum mechanics. So the project is organized in 4 tasks. First of all, of course, we have to study the basic theory. We will use a theoretical approach, which is called non-equilibrium Green function. Then we will see how to translate the basic theory into algorithms to carry out numerical simulation. And of course, we will code the software to carry out the numerical simulations. Then we have to consider that now quantum computers are becoming a reality. So we will explore whether there is any advantage to use quantum computer rather than classical computers to study the dynamics of electron systems. If this is the case, we will develop algorithms for addressing the quantum dynamics of quantum systems in quantum computers. This will be done in collaboration with various partners in the UK. And of course, the last step will consist in doing numerical simulations for materials which have interesting properties and compare the theoretical results with experimental results. So if you are interested in the project, please contact me at my email address, andrea.droghetti@tcd.ie, and thank you for your attention.
Hello, my name is Graham Cross, and I'm a PI at the CRAN Nanotechnology Institute, and I'm also a professor of physics in the TCD School of Physics. I want to tell you today about a project that I'm interested in putting together through the IRC PhD program called Nanopatterning Free Volume at the Frontiers of Disorder. So, in my research group, we investigate the nanoscale mechanical properties of materials, and in particular, we're interested in disordered materials. And I just want to explain to you here a little bit what we mean by disordered materials. Traditionally in engineering, materials such as metals and ceramics have been used, and a big reason for this is because they're in thermodynamic equilibrium. This means that we can use all of the machinery and understanding that's been developed since the 19th century about thermodynamics to understand their behavior. Non-equilibrium materials, and these include materials like glasses and plastics, remain far less well understood, and in fact are one of the principal frontiers of condensed matter physics today. While they're less well understood, they actually tend to be far more tunable and have otherwise unachievable properties. And they're also ubiquitous throughout the natural world. So for instance, most biomaterials are in fact non-equilibrium disordered materials. A key property of disordered materials is free volume. This is extra space between atoms, as I've shown in this picture here, that evolves over time and is responsible for many of their key behaviors. So what's the project? The project that we're going to do involves a technology known as nanoimprint molding, which uses viscous melt flow, say of a polymer film, where we take a pattern stamp, and this is a typical one that we might make, in fact, in the clean rooms that my lab uses in the CRAN facility, and it patterns, say, a thin polymer film on a substrate to look something like this. This technique is very effective for making small-scale structures, but it tends to suffer from adhesion, which is a phenomenon that occurs ubiquitously throughout the nanoscale and limits its practical usefulness. In my group, we're pioneering the use of shear stress via something called confined plastic yield that avoids the high temperatures of viscous melt flow and the adhesion problems. We create unusual stress states to manipulate the structure, mobility, and properties of these disordered materials. And of course, this technique, this way of doing things allows us to continue to use pattern stamps and so on, so that we can create spatial modulation of these patterns for useful applications. So what kind of applications are we thinking of? Well, in the world of disordered materials and glasses, there's a huge amount of technological application. I list some of them here. Some of them you probably have heard of in the news even these days, like solid-state battery polymers, which allow ions to diffuse. The free volume in those polymers is critical to the way in which the charge carriers diffuse. Another big area is amorphous drug formulations. Almost half of all new drug formulations are amorphous now, and it's critical that they dissolve in the body at a rate or a time period that's useful for treating a disease. And it's also critical that they're stable against crystallization, which would radically alter the way that they would diffuse in your body. Flexible organic electronics is a great example of a functionalized glass. Charge carriers diffuse through popping mechanism in these materials. And here's an example here of us using confined plasticity to boost the conductivity in this polyfluorine film by almost a factor of 10 in a controlled spatial manner. There's many others, gas barrier containers for your beer bottles and things like that. These are all examples of non-equilibrium materials with free volume playing an essential role in their behavior. So a little bit about me and my group. The Cross Nanomechanics group focuses really on what's called soft matter, and the two big areas of research that we conduct are the mechanics of 2D materials. And here is an area where we've had some particular success in the last few years discovering self-assembly in these materials. Of course, the other big area is the nanomechanics of polymer glasses and biomatter, where we've had some success in understanding some key size effects in the mechanics of these materials, and as well as processing biomaterials. All of this science in my group is also translated out to technological relevance. And this comes in the form of advanced nanomanufacturing with the nano-imprint technologies that I mentioned previously, and also is applied into various biological systems. So if you were to do a PhD with me, you're going to be using all sorts of interesting experimental techniques. In my lab, in the Cran Institute, I have some of the most advanced nanomechanical testing instruments, such as this three-dimensional nanodenner you see on the left. We also access some of the cutting-edge labs in the world, such as the Triumph cyclotron accelerator, which is used to do a technique called beta NMR, which allows us to do nanoscale mapping of the mobility that occurs in disordered materials. Other places include the Swiss Light Source, where we do nanoscale X-ray microscopy to map density fluctuations. On the technology side, these discoveries that we have at a fundamental level get translated into such things as roll-to-roll imprint that you see here, which allows us to deploy our discoveries in technologically relevant manner. So if this is of interest to you, if it sounds like something you'd be happy to get or learn more about, you can check out my website here, glwcrosswixsite.com. And if you're interested in further pursuing an IRC application, you can contact me at my email, graham.cross@tcd.ie. Thanks.
Hello, my name is Charles Patterson, and I'm going to tell you about simulation of organic materials for organic LED and photovoltaic applications. First of all, why would we want to make an all-organic LED? Well, these materials are cheap compared to organometallics, which contain expensive elements such as iridium or rhodium. They have low environmental impact because it's easy to dispose of an all-organic system compared to, for example, widely used lead perovskites, which contain lead. They're already in your smartphone and expensive TV screen. However, they have relatively low efficiency. So if these are going to replace other systems, such as the organometallics, we need to improve emitters, especially in the blue range of the spectrum. We need to improve lifetimes. We need more efficient emitters to emit more of the energy that we put in as light. And this can be done by molecular design. The knowledge gained will apply not only to OLEDs, but also to photovoltaics because of the reversibility of the absorption-emission process of light. The work is supported by a new SFI grant, which is starting just now in this area. The molecule on the right is one of these TADF, or thermally activated delayed fluorescence molecules, that I'm going to talk about on the next slide. It contains a donor and acceptor part that are shown in that diagram on the right, both as the molecular framework and as the highest occupied and lowest occupied molecular orbitals. So first of all, the electron-hole recombination process. The process of fluorescence is where a singlet-coupled electron and hole recombine and emit a photon, and the process of phosphorescence is where the electron and hole are spin triplet coupled, and here emission can only occur by a weak, slow process which is caused by spin-orbit coupling. Now, as the name suggests, there are 3 times as many triplets as there are singlets, which means that whenever electrons and holes meet in matter, 75% of the time they will be spin triplet coupled and only 25% of the time singlet coupled. A lot of triplet coupled electron hole meetings will end up in a non-radiative process where the energy has been lost. You don't get the energy out as light. So any method of converting triplets into singlets would greatly improve the efficiency of OLEDs. To understand how this can be done, we look at the local exciton and charge transfer excitons in the diagram on the right. If we have a donor-acceptor system, a local exciton is one where the excitation is on one part of the molecule, and a charge transfer exciton is one where the excitation is electron on the acceptor, hole on the donor. Now, in organic molecules, there can be quite a complicated set of excited states in a small energy range, and this is illustrated by the diagram bottom left. We have a singlet local exciton as the first state, which is populated by a photon, a triplet local exciton, and the singlet local exciton may convert to the triplet local exciton by intersystem crossing. However, there are also singlet charge transfer and triplet charge transfer states which are much closer in energy. If we convert into the triplet local exciton, because of the large energy difference, there's no way of converting it back into the singlet local exciton and then achieving fluorescence. But because the triplet and singlet charge transfer states are much closer in energy, of the order of kT, even though triplets form, they can be converted into singlets by a process of reverse intersystem crossing. So this is a so-called thermally activated delayed fluorescence process. In order to describe this, we need to include the many body effects that occur between electrons and holes in matter. Over the last few years, I've developed a code which is capable of carrying out solutions to the beta-salpeter equation and also the time-dependent Hartree-Fock method. The beta-salpeter equation is shown by the series of Feynman diagrams on the right. The polarization propagator pi is the polarization propagator for non-interacting electrons, holes, and holes pi 0. plus an interaction term pi0 k star pi. And the two terms that are in k star are the electron hole attraction, shown by that W term, and electron hole hopping, shown by the Baire-Coulomb term on the right. So the work involves a lot of code development in C and message passing interface, and a lot of numerical analysis, which means handling large matrices. Some of the results that have come out of the code in recent months are shown at the bottom, and you'll see that we're able to predict optical properties of a range of systems: crystalline titanium dioxide, a large sodium cluster, and a bacterial chromophore with great accuracy. If you'd like to read more about this work, you will find it, for example, in these publications at that web address, and you can contact me directly at the email address below. Thank you for your attention.
This is John Gould. I'm the PI in the QSYS group in Trinity, and I want to tell you a little bit about possible IRC projects to work with us. So what does my group do? Well, my group is the Thermodynamics and Energetics of Quantum Systems group. We are a bunch of international theoretical physicists interested in the interface between quantum mechanics and thermodynamics. As you can see, we're a very international bunch, very diverse, and we're a new group that's really expanding rapidly within the school. So what are the research lines? And each line, I would say, is the basis of a potential project for the IRC for a bright PhD candidate interested in theoretical physics. So one of the first lines of research is the energetics of quantum information processing. So namely, we're interested in new devices such as quantum computers, such as technologies which are using the strange features of quantum mechanics to provide advantage over their classical counterparts. And we're particularly interested in the sort of physics question, the theoretical physics question that emerges, like how do we understand the thermodynamic cost of information processing and computation on quantum hardware. So we do theory connected to this question, and this could be the basis of a potential project. The other thing that I'm interested in is actually constructing a theory of thermodynamics suitable for application at the nanoscale. So you know that thermodynamics typically governs the sort of macroscopic scale where you talk about a refrigerator or a car engine, but now imagine engines and devices which are only comprising of a couple of atoms. And therefore, you typically wouldn't expect the usual thermodynamics to kind of apply, as the thing is sort of dominated by fluctuations. And we're very interested in the construction of thermodynamics in that nanoscale domain as a theory in itself. And then we ask very interesting questions like, if we have a device which is made of a number of quantum mechanical components, then how do we maximize various thermodynamics figures of merit, such as power and efficiency? The last topic that I'm very much interested is in the idea of thermalization and transport in complex systems. Probably this is the most fundamental question that we're interested in the group. So in other words, if you have an isolated quantum system obeying the Schrödinger equation, then how do we describe how the various parts of this system sort of start to display thermal behavior? And in particular, I'm very interested in the non-equilibrium scenario where you take a quantum system and you couple it to a number of baths, which may be at different temperatures. And then you get something in theoretical physics, which we call a non-equilibrium steady state emerging. And I'm very interested in the sort of theoretical description of this when the system is complex. So please don't hesitate to get in touch with me. We're interested in people who love theoretical physics, the mysteries of quantum mechanics and statistical mechanics, and are curious about quantum information processing. There are my contact details, and please don't hesitate to get in touch.
Hello, my name is Professor Cormac McGuinness of the School of Physics, Trinity College Dublin, and of the Surface and Interface Physics and X-ray Spectroscopy group. What is my group all about? My group is all about looking at material science, thin films, molecules and surfaces, and in particular using synchrotron radiation X-ray spectroscopic tools to do so. Pictured here is the MAX4 synchrotron in Sweden, and this is the group and some collaborators at a recent experiment at the MAX4 synchrotron and the Beamline FlexPes. A lot of our work in Dublin will involve X-ray photoemission spectroscopy, and I'm going to talk to you about the surface science and material science and thin films growth associated with two potential projects for IRC applicants. So what are these two projects? The first is a study of bimetallic catalysis using surface science and X-ray spectroscopic methods for efficient lower temperature operation of solid oxide fuel cells. Second is a study of the magnetic behavior of iron or cobalt atomic scale nanowires, which are then capped by noble metals. The studies will involve magneto-optics, surface science, and synchrotron-based X-ray spectroscopy. If we look at the first project. So the first project involves material science, surface science, bimetallic catalysis, thin film growth, and X-ray spectroscopy at synchrotron radiation sources. It will involve studies of ruthenium on manganese and ruthenium, ruthenium and nickel on ruthenium, these bilayers, as well as alloys, and manganese and nickel thin films on ruthenium single crystals. We're studying the oxidation and the reduction behavior of these manganese oxides and nickel oxides. This will use in situ ultra-high vacuum chambers in our group in Trinity College Dublin, as well as X-ray and ultraviolet photoemission spectroscopies. What is the underlying theory behind what we're going to study? It's a study of D-band theory regarding how catalysis such as that induced by ruthenium can weaken metal oxide MO bonds and affect the reduction behavior of oxides, such that these are reduced at lower process temperatures, such as might be useful for solid oxide fuel cells. The measurements will be underpinned by synchrotron-based electronic structure studies using soft X-ray photoemission spectroscopy, X-ray absorption spectroscopy, NEXAFs, and X-ray emission or resonant inelastic X-ray scattering of surfaces and the bulk metals and metal oxides at synchrotron sources such as Bessie, which is pictured here. Bessie is a synchrotron in Berlin. So at synchrotrons such as the one in Berlin, we'll be able to perform manganese L-edge X-ray absorption, so we can determine oxide behavior versus metal behavior, which is also given by high-resolution X-ray photoemission, both here in Trinity College Dublin and at the synchrotron. What's our goal? Our goal is to evaluate a bimetallic alloy performance as a cathode material in solid oxide fuel cells, where we'll build prototypes with yttrium, strontium, zirconium layers for fuel cells. One interesting thing about this project is our intention is that we will be using exploiting the new infrastructure available within Trinity College Dublin in the group of Plan and Stamanov for some of this bimetallic alloy growth. This is the so-called trifolium dubium or shamrock 2 chamber, multi-tool thin film growth system with XPS and RPES, and MBE growth and PLD growth, as well as RF DC spotter systems, PLD growth, MBE growth, and an XPS and RPES instrument, which is seen at the far rear of this photo. The second project I'd like to interest people in is, if you're interested in surface science, one-dimensional nanostructures, magnetism, and X-ray spectroscopy synchrotrons, then this project may be for you. This will be studying magnetism in capped iron nanowires, just a few atoms wide, 1 atom thick, grown on a variety of single crystal platinum stepped or vicinal surfaces, which are then capped with gold or other noble metals, protective layers of a few atoms thickness. In the diagram on the right is a schematic of a platinum surface with a 3 atom wide iron wire, which is self-assembles at the step edges of these stepped crystal, which is then capped with a gold overlay. What do we expect to see? we have an expectation that these will exhibit very novel magnetic behaviors. These will we expect to observe a peculiar variety of ferromagnetism with a Curie temperature enhancement of these iron nanowires by as much as 200 to 300 Kelvin. We've already observed this for cobalt nanowires, and this is due to a quantum mechanical coupling called the RKKY interaction involving the conduction band electrons in the gold overlayer. This will involve in situ experimental work in Dublin using ultra-high vacuum chambers, MBE for growth with optical studies, STM, X-ray and ultraviolet photoemission spectroscopy. The magnetic response in situ will be studied by magnetic second harmonic generation and ex situ by reflectance and isotropy spectroscopy magneto-optic Kerr effect, or RASMOC. Synchrotron radiation studies will occur at synchrotron sources such as BESI in Berlin or the ALS in Berkeley, at XMCD beamlines for X-ray magnetic circular dichroism. When we perform X-ray magnetic circular dichroism, we end up probing the element of interest and looking at its magnetic behavior apart from all of the other materials in the thin film growth or in the material which has been studied. We can then compare this to the collective magnetic behavior, which we can measure by MOC. We can do this at a variety of different temperatures, and we can learn a great deal about the magnetic behavior of these one-dimensional systems. So if you have your passport, then you can join our group and travel to the synchrotron sources in Berlin or in Sweden or possibly the United States as well. Okay. So to repeat, my name is Cormac McGuinness. I'd love to hear from you. The email is here, and you can visit our group website. And the two potential projects are the first being the bimetallic catalysis project, and the second being the magnetic behavior of capped nanowires. Okay, thank you very much.
Hi everybody, my name is Stephen Dooley. I'm an associate professor in the School of Physics here at Trinity College. My lab is centered around energy science and decarbonizing. So this is switching our energy system away from a fossil CO2 based energy system, which is currently 82% of the world's energy, to something that is more environmentally sustainable. So a lot of that evolves around fuels, and creating new fuels and knowing how sustainable those things are. So my lab has been, for the last 10 years or so, principally focused on fuel science. So an example of a project we have starting at the moment is the use of renewable electricity to reduce carbon dioxide in water. So water, a very plentiful resource. Carbon dioxide, obviously the climate change inducing pollutant in the atmosphere today. So we can reduce those two ingredients, water up to hydrogen and CO2 over to CO or perhaps methanol, with renewable electricity. So we model the chemistry and physics of this. We make devices to perform this process. And the really key thing is that we look at this model, this energy system model, holistically. So on one side, if this is going to be competitive and viable, we need to have information about the techno-economic performance. So what are the costs in terms of money at each step of the process, and where do we have to create new solutions to minimize those costs? On the other side, what is the actual greenhouse gas intensity of the process? So it's great that we're taking CO2 out of the atmosphere, but how renewable is the electricity that we're using to do that? How efficient are these processes? So this work will start in a few months in collaboration with Professor Kim McKelvey from the School of Chemistry, and it's sponsored by the Sustainable Energy Authority of Ireland. We're looking for more students to join this program. If you're interested in that type of work, please shoot me an email. We have other work. So we're a well-sponsored laboratory. We have some of the biggest companies in the world have come here to do their work with sizable research grants. We're the only TCD member, I believe, of the SFI Energy Research Centre, which is called MARI. It's the Marine and Renewable Energy Research Centre. We have projects sponsored by the International Energy Agency, by the United Nations, also commercialization projects supported by Enterprise Ireland, and various other international sponsors. Some other typical projects that are happening currently in my lab. I spoke to you about the electrocatalytic reduction of CO2 to methanol. We also have a similar process on the acid hydrolysis of biomass to make what are called advanced biofuels. Advanced biofuels are fuels that are not made from fossil or made from food feedstocks. Currently, they don't exist, okay? They're not a sellable product, but the EU has mandated that we use 8% of our transport energy from advanced biofuels by the year 2030. So we have a lot of work to do to meet that target. We have a number of projects there, some fundamental, so examining the chemistry and physics of the mechanism of acid catalysis. We have other projects that are of the commercial variety, so we have a number of patents in the space. Good exciting news for us recently, we have a €1.4 million collaboration with the University of Leeds in the UK, which is basically about deploying these what are called alcoholic gasoline. So that's a funny name for a fuel, but we react to biomass with an alcohol to functionalize the biomass and improve its compatibility with existing infrastructure. So those projects are sponsored also by SEAI, by SFI, and now also by the ESPRC in the UK. We are also interested in a big area I see for the future is in knowing how much carbon dioxide is embodied in a product. So if we take your mobile phone, this was produced with materials and energy, which in the energy system we have today are reliant on a production of carbon dioxide. So what was the CO2 cost in producing your iPhone? Or what was the CO2 cost in producing your laptop, or even the email or this video recording that I'm sending to you today? So the only way we can determine that is actually by calculating the CO2 cost at each stage of the process development. And what that relies on in its essential essence is chemistry and physics modeling. Okay, so we have a project about to start. We've been working on it for a few years actually, but it's coming into a new bout of life. And that's about so-called sustainable aviation fuel, SAF. So you'll see when you book an airline ticket, Ryanair, for example, will ask you to donate €1 or €2 to the CO2 cost of the aeroplane. The question is, how do they know what that CO2 cost really is? Okay, so we don't have good methods to calculate that at the moment. And these are methods that we're developing in our laboratory. And that project has been endorsed by the United Nations Gold Standard. They have contacted us to make a standard methodology for the calculation of embodied CO2 in different types of so-called sustainable aviation fuels. Okay, other projects in the lab, just some examples. So non-fossil energy carriers. One of the big ones that I'm interested in is this molecule here, ammonia. It's similar science to electrocatalytic reduction of CO2, except this time we're going to use nitrogen. So we can reduce nitrogen up to ammonia by renewable electricity. We study the mechanism of that and how we can get it to work better. We write numerical models to describe it. We give the numerical models to engineers to deploy. We also study the conversion process of ammonia with oxygen in a gas turbine combustor. So the idea is that ammonia plus O2 gets converted very exothermically to form nitrogen and water. So you go back to the ingredients that you started with. The problem with this is that it's a very complex mechanism, and in the middle of it here we have a couple of very bad pollutants. So the gas turbine needs to be designed in a way that doesn't allow these pollutants to form, and we only get the products and a large amount of energy. So we use machine learning technologies, and we develop algorithms to solve this mechanism and give the mechanism in a numerical form to the gas turbine engineer. So we work on this with Siemens gas turbines in Canada, and also a different business unit of Siemens gas turbines in Germany, and in collaboration with Cardiff University. So an example of that, the machine learning work, we used to go off and measure or compute with very high levels of electronic structure theory the potential energy dynamics of elementary reactions occurring in gas turbine combustors. This would take typically the order of 10 years. okay, because the conditions inside the gas turbine are so severe, 2000 degrees Kelvin typically. What we've been developing in my lab over the last number of years are machine learning methods to deduce what this effective rate would be. So the example here is on the right-hand side. We develop an algorithm to scan approximately 30,000 different potential numbers for this rate constant, and we compare that to an error function that we derive from engineering data from the gas turbine. And you can see in this example of the data here that there's a clear behavior in where the minima is, and then after a large number of searches that we could only perform with a machine, you can see the optimal number down here in red. So this is really starting to revolutionize how the gas turbines are designed, because it means the engineers can prototype many different combustor configurations and turbine configurations an awful lot more quickly than they used to be able to do. So those are some examples of the things we do. We're interested in decarbonizing. A lot of that centers around fuels. You guys are students. I'm a professor. I make a commitment to you in terms of training. So we produce science. We know that. We produce research papers. We know that. The other thing that we produce are people. Okay? And this is the most important thing that we produce. So it's very important that we make a training commitment to you as students. So my commitment is across 4 topics. The first is science. So you as a student will be trained to within an inch of your life, and we'll have fun doing it on the fundamental aspects of your science, but also the applied aspects of that. And this is very important because it's no use having a bunch of fundamental knowledge sitting in somebody's head. We need to be able to translate that into society. The second thing is communication. Really important now, in particular in the COVID age. We're going to be doing more and more remote working. So I train you quite specifically in how to communicate to a professional standard. That's orally, visually, in writing, and in email, but also clearly and succinctly. So people's attention spans, you may have noticed, are getting shorter and shorter. I hope this video won't be more than 5 minutes. But it's important that we're clear and succinct in everything that we do. The third aspect is organization. You guys are going to deliver a PhD thesis in less than 4 years. You need to be organized and trained in how to manage that project. So that's what we do. I train you very specifically in organizational skills, timelines, supply chains, information chains, and then with a real particular focus on project management. The fourth is research deployment. My philosophy is that it's no good. I do fundamental research. It's no good me restricting myself to fundamental research if I can't conceive of a pathway to deployment to make a benefit for society. I train you in research deployment. So what that means is you're trained in stakeholder engagement, how to have a conversation with external partners, how to have a conversation with other researchers about your science, how to collaborate, but also how to deploy our science and our knowledge in society. So what that means is every month in my lab, you will be reporting to industry. You'll be engaging with industry, having a conversation with them. We'll be having conversations internally about how to commercialize our work, how to configure a startup company. We have conversations all the time with government agencies seeking advice, with industry agencies seeking advice. So those are the 4 training commitments. To summarize, my work is about decarbonizing. If you're interested in physics, chemistry, and numerical modeling that can achieve that goal, please write me an email. Thank you very much.
I hope you enjoyed yourself, found the talks informative, and you have identified several research projects to follow up. The deadline is approaching, so please contact the academics as soon as possible. I would like to thank you again. Hope you all keep well and safe. Hope to see you all next year in Trinity College Dublin.